thank you for all of you for being on time. So what I'm going to be speaking about today, I'm an assistant professor down at the Hermiston Ag Station with OSU. I'm going to be talking about drip irrigation, and mainly this is going to be an overview. Over the past couple months, I've had a lot of growers and people interested in converting to drip, but they needed some of the kind of foundations of the system, the filtration, and some of the other components necessary for the drip. And so I'm doing a trial on drip irrigation in onions, but this presentation, for the most part, is going to be more of a systems introduction, what components are needed and just the various aspects of drip. So with that, drip irrigation has been around for a long time. It might seem like one of the newer advents in irrigation, but realistically, this came from a Polish engineer, Sigma Blas. This was at the end of the 1800s, and he really developed drip in Palestine about 1920. And he was out in a farmer's field, and he realized that there was a dry field in the desert, and there was one lush tree. And so he went out and they were exploring why this tree is growing so vigorously, and they started digging around the root, and they found a leaking coupling and a nice onion-shaped wetting pattern. So that gave him the idea of this low-pressure, kind of low-volume irrigation. So they moved this to the field in about 1930, in which they had just pipe with drills, holes drilled in it, and that was really the advent of drip irrigation. So fast forward about 100 years, we're now using this highly efficient subsurface drip irrigation in some of our production systems. So there's a lot of pros and a lot of cons with this. Even though it's an old system, it's still relatively new in some of our production. This is the highest water use efficiency out of all the irrigation methods. So it's really efficient because we're delivering the water directly to the root zone of the crops. And associated with that, when we're delivering the water to the root zones, we could also be targeting our fertilizer to the root zone of the crop also. So we're establishing a very nice wetting pattern where we need the water and nutrients to be. And along the same lines of that, when we're applying those nutrients and water to the root zone, we're going to be reducing a lot of the leaching that is corresponding with that. So the water quality hazards can be reduced with using drip irrigation. And in this area, the water quality is a big issue with the nitrates in the groundwater system. Because we're applying the water from beneath and not coming down from above, we're going to have reduced disease pressure, as commonly found with a lot of the overhead irrigations, along with reduced weeds. We're optimizing the use of the land because we're able to fill the entire plot with drip, opposed to just a circle in the middle of a square. And then one other important aspect, which is commonly not thought of, is that you could operate in the fields when the drip irrigation is running. Whereas normally you would not be out when a pivot's running, but you can be in the fields when the drip irrigation is currently active. But on the other side of the spectrum, drip irrigation is high cost. There's a lot of expenses to go into these systems, especially initially when you're getting the filtration and the manifold set up, as well as installing the drip lines every year and removing them. Also a lot of maintenance that goes into this, which I'll touch on in a bit. Establishment of direct seeded crops. Some of the growers are establishing their direct seeded crops under the pivot or with hand lines, and then once they're established, they come in and they run the drip lines. However, there's a lot of work in this, kind of in this realm, and I think that that's going to be overcome pretty rapidly. Monitoring can be difficult because you're not able to see if there's non-uniform irrigation because it's underground. And so what we're going to talk about here is there's a lot of components that I mentioned that go into making the drip system, and we're just going to focus primarily today on different types of filtration and a few different types of injection. We clearly don't have time to go through all of it, and then we'll have some time at the end where I'll talk about some of my work with onions. So with these drip irrigation, we have these little micro channels in which the water is funneled through. That's where the irrigation water is coming from. So these small channels, they pose a big problem when they start to get plugged, and plugging is just a natural phenomenon of passing water through small channels. So there's three primary reasons in which we get the clogging. One is physical particulates, such as sand or clay or silts. Biological, that's algae or bacteria, or chemical precipitates. So depending on your specific site, in which we'll discuss more, you need to develop the filtration for your site by doing a water test and seeing which of these, or maybe all of them, pose the biggest challenge, and then design your filtration for that. So first off, we'll talk about screen filters. These are highly adaptable. I really like these screen filters. Within the body of this tube, there is either a perforated metal tube with a sock over it, a mesh sock, or it's just a screen in itself. And that's, the screen is generally adjustable to the mesh size depending on the type of filtration you need or the intensity of filtration. These are strongest with the inorganic material, so the particulates of sand and clays. They're not as strong with the biological, with your algae. They tend to clog up more rapidly. These are, you can go large size up to 6-inch inlets. I run them on my experiments because they're relatively small. I'm only running maybe a quarter of an acre. And sand filters aren't that efficient when you're running very low flow through them. So this is a good option if you have smaller gallon per minute systems. Disc filtration. I haven't had very good luck with the disc filtration. So maybe some of you have, but I don't recommend this. Supposedly you could get great filtration down to about 25 microns. And to put that in perspective, a human hair is around 75 microns. So you get good filtration, according to the literature. But it's not, if you have biological, if you have algae, it tends to be sheared. So it's not really the best type of filter for biologicals. Supposedly it's strongest on the particulates, but again, I haven't had great success with these filters. Sand filters are generally the gold standard in this area. This is, it's strongest for biologicals, so algae. It's really good for filtering algae. Depending on the type of media you put in, whether you put in a smaller form silica or a coarser silica, you can increase the filtration. So these can go up to about 250 mesh filtration. You can put them in tandem, or depending on your specific needs, you could also put, say, a screen filters and then the sand filters. If you have a lot of the silts in your water and a lot of algae buildup, you could run 2 filters in tandem. So sand filters are generally the common around this area. And so why do we need these filters? We need it generally because of 3 reasons. The sand, as I mentioned, the biologicals, and the precipitates. So one way to, before you come into a site and you're choosing your filtration, do a water test. And so bicarbonate is one of the main issues that we have when we get the calcium buildup. As you see, I'm sure we've all seen that. When your pH is above 7.5 and you have over 120 parts per million of bicarbonate, that's when we'll start to see this formation. It's relatively easy to rectify. If you just acidify your water, then we can knock the calcium out pretty quickly. But once it starts building up, it's hard to control afterwards. So be alert, be on the watch, and if you see some of this buildup, take care of it right away instead of coming in after the fact. Iron, I did a lot of my drip irrigation work in Hawaii where iron was a big issue. Does anyone have drip irrigation and iron problems out here? Yeah, I didn't think so. So don't really need to worry about iron. If you did have it, phosphonic acids are a good solution to keep it in solution. Biologicals are generally the biggest issue, getting algae, especially if you're drawing from a surface water source. Sand filters, as I mentioned. However, if you need additional, which you likely will need additional filtration or products to help clean the lines, you could use different copper-based biocides. I've had most success with the ROS line cleaners. They're reactive oxygen species, so they pull electrons from the biological material and kill it that way. A couple products which I use are the Sanidate 5. It's from BioSafe Systems, and it's been really effective in cleaning out my lines. However, you could also use different chlorine products or use acidified water. When you do think about if you do have any issues or you're doing your routine maintenance, try to switch up and do combined approaches. it's always best to try to be switching your mode of action. Not necessarily like resistance in chemicals, but coming at it from multiple fronts is usually the best approach. As well as routine maintenance. Don't wait until you have a clog, come in earlier and take care of it beforehand. So when we talk about some of the injection potential, you guys could come on in if you open this door here. So the three methods with injection, there are three basic steps: dissolving, injecting, and delivering. Some of the reasons we could be injecting chemicals, such as chemigation, or it could be injecting fertilizers, which is the most common. In this trial and the Willamette, they were looking at blueberry fruiting potential, and from year 3 when they started the fruit to year 7, they were comparing no fertilizer, fertilizer injected through the drip system, fertigated, and then no fertilizer, and then a comparable granular fertilizer. So what they saw in the green was the fertigated. They had in each year 12 to 40% more yield with the fertigation product. And again, because that's delivering it right where it needs to be and it's highly efficient. So granted, this isn't a veg crop. There's been a lot of similar response in the veg crops. So a few different types of injectors. First is the batch tank. This is a very simple approach to injection where you put your entire slug of fertilizer in the ratio in the tank, and then as you run the line, it essentially just pumps it out like a hot water heater would work at your house. But I wouldn't recommend these, especially in this area, because if you see the concentration over time, we have the highest concentration of fertilizer coming out right at the beginning of the fertigation cycle. So that doesn't make a lot of sense. If you're delivering this slug right up front, and then you're going to be running the system for another couple hours, then you're just going to move all of that away from the root zone. And that's going to contribute to the leaching, especially nitrate leaching and any fertilizer leaching. So environmental hazards, and you're not getting the most bang for your fertilizer. So I don't recommend these purely because of the lack of uniformity. Venturi injectors are really useful. They're cheap. They work by utilizing the flow of the water, and they create a vacuum, and that's what pulls your product. These can be used in right in the manifold, or you could run a bypass line through it. They come in anywhere from 1/2 inch to 2 inch. So again, pretty adaptable. They're simple, they're cheap, they provide a fairly uniform rate. However, they lack some of the accuracy and flexibility that you might need with some of your injection. The positive displacement injectors are really some of the best options. They run electric, hydraulic, magnetic, a few different actual components inside, piston driven. These can be easily integrated into an automated system, and when you're using drip, automation is really the way you want to be. So they're easily integrated into an automated system. They're extremely precise and easily controlled. However, they are more expensive than something like a $10 Venturi injector. And then we have all the moving parts, so there's going to be a lot more maintenance on these. I generally, in my trials, I use this type of proportional dosing pump, which is a dosatron. And this works great for my uses, and so I recommend these. Granted, a lot of your operations are significantly bigger than anything I do, but they do upscale them, and you can put these in tandem. So this is, again, it runs off of the flow of the water, and they're extremely flexible. You can adjust the dosing ratio extremely easily just by twisting the adjustment on the bottom from, say, 1 to 50 ratios all the way to 1 to 1,000. So depending if you're doing chemigation or fertilization, there's a big range that you could achieve with these. However, they're a bit more expensive, and you have to maintain them, but it's a good option if you want flexibility. But whenever you are doing any kind of, especially chemigation, you need to be sure that you check the local statutes for backflow prevention. Generally, you need a chemigation license, and always you need to have backflow prevention. If you're in Oregon, look at the OAR 690. Washington, the WAC 16, and Idaho ADAPA 0203. And those will give you the up-to-date statutes on what you need in terms of your backflow. So with any of these systems, whether you're using a pivot or this highly efficient subsurface drip irrigation, these are no better if you don't manage them properly. Drip irrigation isn't the most highly efficient if it's improperly managed. So this comes down to using sensors and automation along with your agronomic knowledge. All of these fancy sensors don't mean anything if it's not tied together with your knowledge of cropping systems. So these are just some options for your irrigation management. I'm sure a lot of you are familiar with evapotranspiration. So the first is the weather base, where we look at the evaporation from the cropping systems. We couple that with a crop coefficient, and it will give us an estimate of water losses for our specific crop. And then we will replace that with the drip irrigation. If you don't have weather stations accessible, I use this Agromet. Just Google Agromet weather stations. We have them all around the Pacific Northwest, so you can get accurate weather data. You can get the models of evapotranspiration, as you see here, and it's all free and it's all online, as well as the crop coefficients. So all of your information can be found here on the Agromet. If we look at the soil measurements, there are two main measurements of soil moisture. One is volumetric, and another is soil tension. A lot of times these are used interchangeably, but they're really very different measures. If we look at volumetric water content, it's generally an amount of water in a given area of soil. So it essentially is a percentage. So it's how much percent water in an area. Whereas the soil tension is a value of resistance of water in the soil profile. And so this is, in my opinion, a stronger measurement of soil moisture because it's more along the lines of what the energy the crop roots are needing to achieve the water. So I like soil tension opposed to the volumetric. Whatever way you're going to do it, there are a lot of good options. For the volumetric, there's time domain measurements, neutron. These are more expensive sensors that generally require calibration, but they're very accurate along a big range of wet and dry. Whereas the sensors that I use, these granular matrix sensors, they're a little weaker in coarse soils when it gets really dry. So these are the sensors I use are relatively cheap. They're about 24 bucks. So you can put a lot of these in the field if you need be. And they give accurate readings. They last for a few years if you treat them appropriately and clean them. But they don't require calibration, and it's just a real easy sensor to achieve some of your soil tension readings. And again, both of these hook up really easily with an automated system. So automating your drip with these type of sensors for an onset is relatively straightforward. The plant-based measurements don't make a lot of sense in veg crops. This would be, a pressure bomb would be measuring leaf water potential, and this would be more useful in something like a blueberry, a perennial system, or wine grapes, which will actually see the water and the stress the leaf is under. Remote sensing, again, doesn't make a lot of sense for irrigation management. However, it's useful if you're going to look at uniformity. So if you're going to do an aerial image of your field, you can see if the drip lines are not uniform, or if there's dry spots or wet spots. So that's where that would fit in. Perfect. So now I'll talk a little bit about a trial that I've been working on. I started last year, and I'm going to continue this for the next few years. And the main objective this last year was just to get the track of all of the equipment and get it working together and figure out how it functions. And I was trying to evaluate the subsurface drip and looking at 2 different emitter flow rates and 2 different onset thresholds of irrigation timing. And then I wanted to do a model of what's happening underground, so I can see where the wetting pattern is in the onion root systems, and if we're able to achieve the appropriate wetting pattern for an onion bed. And then in the future, I did some of this last year, but the data wasn't very reliable. But we'll be doing more intensive program for trying to capture the nitrate leaching to see if it's much more efficient with the different flow rates and drip irrigation. So this was conducted at the station down the road at Herrick in a very coarse soil, the Atkins sandy loam. So the treatments were the onset irrigation. The soil tension is measured in centibars, or the equivalent measurement is kilopascals. So 10 centibars and 20 centibars, two different onsets. The lower you get to zero, closer to zero, the wetter the soil. The higher the number, the drier the soil. And then I was looking at two flow rates of, essentially these are low and ultra low flow rates. The ultra low would be 0.07 gallons per hour and 0.13 gallons per hour. And at each irrigation time, I was delivering 1/10 of an inch. So this was set up in somewhat of a standard bed configuration, in which the drip line was placed down the middle of the bed, 2 to 3 inches deep with 8-inch emitter spacing. On each side of the emitter, the onion rows, 2 double beds starting at 4.5 inches were placed. So we had the 2 double beds with 9 inches in between the starting of each onion row. So what we saw in the earlier season, when the water demand wasn't as intense, the onion height was a little more, they were a little taller than with the 10 centibars, which is the wetter irrigation. The 20 centibar, the drier, both the high and the low flow, the onions were a little smaller and had some establishment challenges. But when we looked later on at the yield at the end of the season, once we had some more of the water stress and we needed the water for the development, we saw that the 10 centibars, that's the wetter treatment, clearly was better than the 20 centibars, in which we almost had no onion bulb formation. So based on this is just preliminary. We're going to do more treatments next year. But we see that the 20 centibars is far too dry to keep your onions at, opposed to the 10 centibar onset. And this is, in Ontario, a lot of the literature that is published, the onset should be 17 to 20 centibars. So the soil type makes a huge difference in when you want to be having your onset. If you have a denser soil, then you could run it a bit drier because you have more movement between. With a coarser soil, you need to run it at a wetter status. So again, just to visualize, with I'm calling them low and high flow, but in reality they're low and ultra low. We have our low flow, you see some establishment problems, weaker onions. With the high flow, we have a somewhat traditional looking bed. So when we look what's happening below the surface, we see that we have our low flow and our high flow. Now what's going on here, this is an onion bed, as you see what we have up here, the 2 onion rows. Beneath the ground we have the sensors placed in a grid pattern at 2 inches, 8, and 16 inches, and then throughout the bed laterally as well. And that's what we're seeing in each of these images, is that sensing profile. So this is showing the time at onset, and then the T is how many hours after onset. So what we saw with the low flow is that around 1 through 4 hours, the water is slowly moving down to about this 8-inch range where we would expect to find our onion roots. And then it's saturating more within that profile over 8 hours, and then it's moving down slowly with a deeper infiltration around 16 hours. So we're getting a nice pattern, but we're getting more infiltration. When we look at the higher flow, and again this is both 1/10 of an inch, same amount of water, just a different flow rate. When we look at the higher flow, we see a bigger slug coming down, because it's higher flow, that's pretty obvious. At 2 hours, we see that slug coming down, and then we see it really moving laterally and filling the profile after 4 hours. So we have more lateral push, which makes sense. You have more water coming out. It pushes, opposed to just floating down through the coarse soil. So we get a stronger wetting pattern, and this would make sense if you're trying to do more direct seed establishment, if we can get more water up towards the surface. And then what we see, which is different from the high flow and low flow, is that we have less infiltration to 16 inches. We generally see that that slug of water is pushing throughout the upper profile and not moving down. So this is a positive This is positive if you look at nitrate leaching and fertilizer losses as well, because we don't need the water down at 16 inches. The roots aren't really functioning in that area, so why would we be pushing water? So in conclusion, drip irrigation is a highly efficient, highly effective means of irrigation that is needed to be site-specific. So your topography, your soil type, the water testing, do water quality tests before you come in so you know what type of system to build. It's not the most efficient technology if it's not managed properly. So this is the very efficient if you manage it properly, automating the system with some of these various sensors that I spoke about. Even though it's higher cost, the returns are recouped with a lot of the economics with this. And in sandy soil, based on some of the work that I did last season, in order to get the lateral spread across the onion bed, it's best to have a higher flow rate, such as the 0.13 gallons per hour. And that pushes the water, and you don't get as much leaching. And again, I'll be working more on this in the next couple of years, and so I'll be refining these recommendations. So there's more to come. With that, I think there's a couple minutes for questions. Tim.
Which sensor depth were you using, Scott, for the trigger to irrigate?
Yeah, so on the, you saw that grid pattern? We were using 8 inches that was the decision-making sensor. So in each of the plot we had that grid of sensors, and they were all used for modeling the water, but that 8-inch was actually making irrigation decisions.
Do you plan on doing anything more with heavier type soils? Because that's where we're running into issues with, is pushing the water laterally through the heavier soils on the farm. Are you planning on doing any more research into that anytime soon, or?
I will be doing a couple trials this year, but it's mainly going to be focused on the sandier soils. With the heavier soils, generally it's not as much of an issue to push it laterally, but I'll be doing, like I said, the Atkins sandy loam is generally the soil I'll be using. I'm hoping to do some other grower cooperative trials this year, so we might have more information on that. But if you follow up, we could talk about the specific type of soil. Yes?
Yeah, on that trial, you were putting the same amount of water just at a shorter period of time at higher volume, right?
Yep, that's right. We're just delivering 1/10 of an inch at each irrigation cycle.
Did you do any trials with using water penetration products to try to get more lateral?
Nope. We're doing it just this year, just with the water from the source. We weren't adding anything else to it. And there are some products that have been reported to move the water laterally, but we didn't need it when we were running it that onset. All right. Thank you.